Hello everyone and welcome to today's theory prep video. Today we'll be talking about infinite cardinalities and we'll also be doing a little bit of a longer proof. So let's start where we left off last video. We were talking about, do there exist infinite sets that are not the same size as the natural numbers? Because we showed that the integers are the same size. So are there infinite sets that aren't the same size? Because otherwise, if all the infinite sets are the same size, then we didn't really need to do all this work to make all these definitions. We could have just said, well, for a finite set, your cardinality is how many elements you have. And for an infinite set, then your cardinality is just, we'll just write infinity. And we'll see today an interesting result, which is that there are infinite sets that have different cardinalities than the natural numbers. And that's a really interesting result because you wouldn't have expected there to be multiple types of infinity. I think most people just think of like one type of infinity, but this actually says that there are infinities of different sizes. But before we get into that, there are actually a lot of sets with the same cardinality as the natural numbers. They come up a lot, and so it's useful to have a definition to summarize that. And so this is definition 8.1. We say a set A is countably infinite if there exists a bijection from the natural numbers to it. The reason we say it's countably infinite is because if we let AI denote f of I, then the items A0, A1, A2, A3, all the way, etc., etc. Well, first, since this is a bijection, and therefore it's injective, so we know each of these elements is different. And then second, we know it's a bijection, so it's surjective. So if we keep just going to infinity with this, we'll get all the elements of A exactly once. And so we can basically count out the elements of A. You can order them like a 0 at the first one, etc., etc. And that's why we call that set countably infinite. So that's just an important definition to know. And now let's return to our question. So our question was going to be, how can we make an infinite set that's like even larger than n? And so what we saw was that basically the integers are sort of twice as large as n, right? Because you kind of take all the positive numbers and you add a bunch of negative numbers, which are, so for every positive number, you add another negative number. And we saw that sort of doubling the size didn't really change the cardinality. So maybe we can increase the size in an even larger way, and that will help. So to do that, we're going to use what's called a power set. And a power set it can be motivated by, how can we increase the size of a set a lot? Or it could be motivated by like, oh, you have a group of people, how many subgroups of those people could you have? Or a lot of times you want to look at subsets of something. And so the power set of some set A, denoted by, we use this blackboard P of A, is the set of all subsets of A. And that might be a little bit confusing, so let's give an example. So the power set of 1, 2, 3 is first the empty set, nothing in it, then the set with only 1 in it, then the set with only 2 in it, the set with only 3 in it, the set with 1 and 2, the set with 1 and 3, the set with 2 and 3, and finally the set with 1, 2, and 3. So it's all the subsets, including the subset with everything and the subset with nothing. And it might be a little bit easier to understand some things about the power set if we write these as binary numbers. What do I mean by that? Well, for every subset of 1, 2, 3, basically what we're asking, and we can completely characterize that subset by just asking, well, is 1 in it, is 2 in it, and is 3 in it? And we can represent that as like a little binary string, right? So it has 3 bits. The first bit is 1 in it, the second bit is 2 in it, and the third bit is 3 in it. So for example, the empty set would be 0, 0, 0, because neither 1 nor 2 nor 3 is in it. The set containing just 1 would be represented by the string 1, 0, 0. 2 would be 0, 1, 0. Then we have 0, 0, 1 for 3. Then for 1, 2, we have 1, 1, 0. For 1, 3, we have 1, 0, 1. 2, 3 is 0, 1, 1. And 1, 2, 3 is just 1, 1, 1, right? And so this is a little bit of a cleaner way to write this. Instead of writing sets of like many different sizes, every single element is now represented by a 3-length binary string. And second, this also gives us an easy way to tell, well, since there are 3 elements here, then we expect so if the size of A, right, is equal to, let's say n, then we know that the size of the power set of A will then be equal to 2 to the n, right? Because we can write it as all of the binary strings of length n and we know that there are 2 to the n of those strings. So that's helpful because taking 2 to the nth power is a much larger operation than like adding 1 to n or doubling n, which is what we did when we went to the integers. So maybe this will get us a larger size of infinity. So in that case, what we would want to do is consider the power set of the natural numbers. And obviously, we can't actually write out the power set of the natural numbers, but again, using this trick where we associate every element with a binary string, we can just represent the power set of the natural numbers by infinite length binary strings. What do I mean by that? So one subset of the natural numbers might be the numbers 0 and 1. And that would be represented by 1 because there's a 0, 1 because there's a 1, 0 because there's no 2, 0 because there's no 3, and zeros, etc., etc. We might have some other subset, which would be like 2, 4, 5. And in that case, this would be represented by 0 because there's no 0, 0 because there's no 1, 1 because there's a 2, 0 because there's no 3, 1 because there's a 4, 1 because there's a 5, and then zeros all the way down since there are no other elements. And we can use this infinite binary string representation, right, to represent any subset of the natural numbers. For example, like the evens. Well, that'll just be 1 because 0 is even, 0 because 1 is odd, 1 because 2 is even, 0 because 3 is odd. So it'll just be an alternating string of 1s and 0s. So we see that basically every possible subset of the natural numbers we can write as an infinite length binary string. And so, in fact, there's like sort of a one-to-one correspondence between them, right? Because if you have some infinite length binary string, well, if you use each bit to indicate should we include 0, should we include 1, should we include 2 in our subset, that characterizes an element in the power set of the natural numbers. So now that we've built up some machinery, we're going to try and prove that there does not exist a surjection from the natural numbers to the power set of the natural numbers. And we actually say that the absence of a surjection from one set to another set means that the former set has a cardinality which is strictly less than the cardinality of the latter. And let's make sure that this definition makes sense. Well, indeed it does, because remember, we defined if there is a surjection from set A to set B, well then the cardinality of set A is greater than or equal to the cardinality of set B, because that implies that the elements of A can cover the elements of B, which means that they must have at least the same, if not a higher cardinality. And so then if there doesn't exist a surjection, well, we would expect the opposite relationship to hold. In other words, well, if it's not possible to cover the elements in the second set, well, then there must be fewer elements in the first set. That's sort of the intuition behind this definition. Note that sometimes definitions is defined in terms of like an injection existing and no bijection existing, but up to some assumptions like axiom of choice and stuff, it's the same thing. But for our purposes in this course, I think this is a little bit more intuitive way to approach it. So non-existent statements are sometimes hard to prove, and it's easier often to prove universal statements, which we know how to prove. So we'll rephrase this. To say that there does not exist a surjection is the same thing as saying that every mapping between n and the power set of n is not surjective. So we'll proceed by proof of universal statement, and we'll just fix an arbitrary f, mapping the natural numbers to the power set of the natural numbers. And so now we want to show that this is not surjective. What does that mean? Well, if f is not surjective, that means that we want to show that there exists something in the range, right, some m, in the power set of n, such that f does not cover m. And so let's write this a little bit more mathematically. We can rewrite the first part. There exists some m in the power set of n. And if we say f does not cover m, what we really mean is that for any natural number, f of n is not equal to m. That's what it means for f to not cover it. It means you can put anything into f and you still won't get n. So we'll write that as for any natural number, f of n is not equal to m. So this actually helps us see a correspondence and a trick for rewriting like quantifier statements when you have to negate them. So what we wanted to show was f is not surjective, right? And so right here I wrote not, this is a logical symbol for not, and then this is a definition of f being surjective, right? For anything in the power set, there's a natural number such that the natural number maps to that element in the power set. And we just negated it, right? Just sort of by thinking through logically what it means to not be surjective. But this shows a general trick. So the general trick is when you have not of some quantifier statement, first you negate the part inside. So we took f of n equals m and we turned it into f of n does not equal m. And then for every exists, you just put it in a for all, and for every for all, you put it in an exists. And so just remember not to blindly apply this trick, but it can be helpful in cases that are like really complicated with quantifiers. But after you apply it, make sure it makes sense, the way you've reframed the statement and how those are logically equivalent. So this suggests a proof strategy, right? It suggests, since we're trying to do an existence proof, we have to find some infinite binary sequence, right? Because that's how we're representing the elements of the power set, such that it's not equal to any f of n. So what might we want to do? Well, maybe our first step is to just write out some different values of f of n, right? You can imagine, so we fix some f, and f of 0 will give us an infinite binary sequence, so we can write out bit 0, bit 1, bit 2 in some table, et cetera, et cetera, et cetera. And then same thing for f1, f2, f3, f4. And we want to create some m that disagrees with every row of this table, because it's supposed to disagree with f of n for any value of n. And what does it mean for m to disagree, or for two infinite binary sequences to disagree? Well, it means they differ in at least one bit. As long as they differ in one bit, that's enough to make them not equal. Because if you think about the subsets that those correspond to, that means that one subset contains an element and the other one doesn't, in which case they can't be the same subset. So this suggests maybe another strategy. So we want first m to disagree with f of 0. Let's have it disagree with bit 0 with f of 0. So f of 0 is 1 here, so we'll make m 0 here. And then we need to disagree with f of 1. Let's have it disagree on bit 1. So we'll put a 0 here. That'll disagree with f1. f2, again, we'll put 0, and that'll disagree. And for f3, we'll put a 1 here so that it disagrees on bit 3. And for f4, we'll put a 1 so it disagrees with f4 on bit 4. And you can see why this is called a diagonalization argument, because basically what we're doing is we're just taking the negation of all the entries on the diagonal of this, and we're using them to define m. And I claim that m, no natural number, will map to m. And we know this is true because for any natural number, take for example like 100, the m is defined such that its 100th bit is the opposite of the 100th bit for f of 100. So for any natural number, like n, the nth bit of m is defined as the opposite of the nth bit of that infinite binary sequence. So therefore, they can't be the same thing, and m is different from every single f of m, and therefore we've proven what we want to prove. So this is definitely the hardest proof that we've done so far in the course, and definitely worth thinking about and making sure you sort of understand how each step sort of fits together. But it leads to a really cool result, right? Because it tells us that there are multiple sizes of infinity. There's not only countably infinite sets, but there's uncountably infinite sets. There are infinities that are larger than just the natural numbers. And that's something that we definitely would not have expected.